So welcome to the next video. In this video, we'll talk about different types of models available in the lithium ion models library within PyBaMM. So firstly, we'll import PyBaMM and list down all the available models within the lithium ion library. We can see a list of different items here. Now, it consists of some base variants or basic variants which were kind of legacy models within PyBaMM. And then it also consists of the newer models which are the production-ready models, which includes DFN, Doyle-Fuller-Newman Model, then there's MPM, which is multi-particle model, and so on. Now, broadly, these are the common types of model being used widely, which includes SPM with the electrolyte dynamics, DFN. SPM is for single particle model, where a single particle is used to represent entire cathode, and similarly a single particle for anode. Then we have the full P2D model, which is also known as DFN, Doyle-Fuller-Newman model. Then there's multi-particle model, which allows various size of particles. And then there is composite DFN, Yang 2017, and 3D thermal SPM. These are the commonly used ones. And then let's see what are the differences. So particle diffusion is present in most of them, in all of them. And then electrolyte diffusion is absent in SPM and 3D thermal SPM. Thermal model is absent in SPM and SPMe and is optional. By default, it's turned off, and you need to turn it on through some settings and parametric setup. And the thermal model is 3D, as the name suggests, in the 3D thermal SPM model. In terms of degradation, it's absent in SPM and SPMe. It's set to optional in DFN, can be turned on as needed. Similarly, in multi-particle model MPM and composite DFN as well. Yang 2017 is a special model which allows lithium plating, and it's absent in the 3D thermal SPM as well. Now talking about multi-particle sizes. So as the name suggests, it's only possible in the multi-particle model, and the composite electrode is possible in the composite DFN. So now, firstly, let's define the. In this study, we'll proceed with the 3 most commonly used ones, and then probably discuss multi-particle model in one of the later videos. We'll also discuss electrical equivalent model in the next video. So for this analysis, let's stick to DFN, SPM, and SPMe. So we'll call it using PyBaMM.lithiumion.dfn. And then similarly, we'll call the other two as well and store it in the respective lowercase variables. Let's run this. Next. Now, if you want to print all the variables present or accessible within a particular model, we can do DFN the model name dot variables dot keys. So that will print all the dictionary, all the keys in the dictionary, and it is a very long list and can be hard to read. So we can also use the for loop with the print statement, which can help with better organization. So the print statement by default in Python has a line break at the end, which allows each print statement to be printed in the next line. So again, we end up with a large number of variables, which is hard to identify. So there is a nice option available within Python. So we can insert a if loop within the for loop. So for key in dfn.variables.keys, so it will basically iterate through all the keys available in this dictionary. And then within those keys, it will search for the keyword of interest. In this case, let's say we are looking for electrolyte related parameters. So we define the string as electrolyte. If electrolyte and keys, then only will print the key. So with this, we'll be reduced to only the variables which has electrolyte in the name, right? So this way you can filter out and find out the respective variables. Now let's probably look at one other use case where you would like to compare different models and some of the results like voltage and temperature. So for that, we will define models with a list, and then in this solutions section, we'll basically define an empty array or an empty list. Now let's define Chen 2020 as the parameter set value for the study. You can pick the other one as needed. So Chen 2020 is equals to PyBaMM.parameter values, and then we'll use the string Chen 2020. This was discussed in the previous video. If you have not watched that, please revisit. It might give some more background about how to set this up. Now, once we've selected the parameter, next step would be to iterate through all these models in the list. So for model in models list, we'll do the following. We'll create a simulation, sim equals to pybam.simulation, and pass the model. So it will loop through each of the model and then pass it through this and run the simulation. And then parameter values will be set to Chen 2020. Then sol equals to sim.sol will solve for 1 hour, 0 to 3600. And then finally, in this empty list, we'll append all the solutions. So sols.append sol at the end of each model iteration. So this way we'll end up getting 3 solutions in the sols list. Let's run this. Now let's plot terminal voltage for the 3 and compare. So for that we'll import matplotlib.pyplot splt, store the entries of sols 0, which is dfn. So this is 0, this is 1, and this is 2. So the 0 values correspond to dfn, 1 for SPM, and 2 for SPMe. And what we are storing here is T, which is time, and P, which is terminal voltage. So once we run that, we can see that DFN and SPME kind of mostly overlaps, whereas there is significant difference as compared to SPM. Now, let us look at another aspect, which is to find the submodels within a given model. This will help us identify what are the tuning submodels available in, let's say, DFN, so so that we can adjust them as needed. So for keys in dfn.submodels.keys, we'll print the keys. You can find the list of keys here. Now again, similar to what we did earlier, we can search for specific keys like electrolyte, and we find these 3 values. Now let us look at electrolyte diffusion between the 3 models and compare. If we do dfn.submodels electrolyte diffusion, then we end up getting electrolyte diffusion.full, which means it follows a full diffusion process. On the other hand, SPME also gives a full diffusion model, but the SPM model uses a constant concentration. It doesn't include electrolyte diffusion, which was also discussed earlier in this table. The electrolyte diffusion will be missing in SPM and 3D thermal SPM. Okay, let's move on. So this way you can also compare submodels between different models that you would like to compare. Now, as a last step for the given video, let's see how we can include thermal, because we saw earlier that thermal by default is optional in DFN, SPMe. In DFN, it's not present in SPMe and SPM. So with a DFN model, let's try to run a case with and without a thermal model. So within the DFN model, let's set up and give it a name for easier identification. So we'll give DFN equals to PyBaMM.lithiumion.dfn, name equals to, and this is just a custom string which might be used later for legend creation automatically. When we create a plot with this model, we'll have the legend DFN without thermal. So that will help us in ease of reading plots and without too much complexity on the side of setting up the legends manually. Now, let's use another name dfn underscore thermal for the one where we will again call pybam.lithiumion.dfn, but within the brackets will turn on, will point to the options dictionary and then set the value of uh, the thermal setting to be lumped instead of ignored. So this is how you can change the thermal settings with, within any model which supports thermal modeling. So the options would be set equals to curly brackets thermal, and then lumped string would be used to assign the value to thermal model. And then lastly, we'll give it a name equals to lump thermal. Finally, we'll put both of these models in our model list. And then also similarly, as we did earlier, create a sols empty list, start the for loop for model in models, sim equals to pybam.simulation, model parameter values equals to gen 2020, sol equals to sim.solve, will solve for 1 hour, 0 to 3600, sols.append, sols will add each of these models in the sols empty list. We'll end up with two models with two solutions, one for DFN, one for DFN, uh, first one for DFN without thermal and the second one for DFN with thermal. And then finally for key in DFN dot variables dot keys, uh, let's print if voltage in key and or temperature in key. If either of these condition is fulfilled, we'll print. So that means we're just trying to print out what are the names available for voltage and temperature related plots so that we can plot them in the next step. So here we have a list of all the plots available by the name voltage and temperature from which we can find out. For the sake of simplicity, I'll just move ahead with the plots of interest, which you can also identify in the list above or in the output. So we'll plot the terminal voltage and cell temperature in degrees Celsius. So let's run this. This is, we are calling here pybam.dynamic plots, which is the uh, which is a pre-built dynamic plot library supported by PyBAM, which also allows sliders to change the location, and then a dotted line appears to represent where we are in time for time-based plots. The second plot is cell temperature, and since uh, it, it is a P2D model, DFN model, so it has a thickness discretization along with radial discretization. So the x-axis here for temperature is thickness, although we will not have variation along the thickness direction as we are not solving the 3D DFN model yet, but by default it appears in the following form. So you can see how over time the dotted blue line, which is the lump thermal model, is representing the change in temperature. We could have also plotted a time-based plot instead. So you can find that from this list of temperatures, and you can also maybe reduce it to exclude the voltage keys. Okay, so Lastly, let's look at plotting it with matplotlib instead of dynamic plots. And this is how the temperature evolution occurs for the given run. So again, we have done the same thing. T1 set to time, capital T1 set to volume average cell temperature in degrees Celsius. And then we are doing the same for the DFN thermal model, plotting them together in the same plot. And we can see that the DFN without thermal is a flat line as expected, and the initial temperature was 25 degrees Celsius. On the other hand, lumped thermal is uh, basically a single lumped mass model which solves in the background equations like heat balance, which basically includes the convective heat transfer HA delta T and the heat absorbed, which is MCP delta T based on the material property, MCP dt by dt, and also finally the balancer would be the heat generation. So the heat generation Q from the model, because of I square R and reversible heating, would be balanced by the sum of the temperature rise within the battery due to absorption plus the heat released with convection. So this is how the lumped model would behave, and you can see the temperature evolution. Hope this video was helpful, and thanks for watching. See you in the next one.